Okay, so we have been talking about mass spectrometry. We have been talking solely about electron impact ionization mass spectrometry so far. And we talked about how the ionization takes place. We talked about the molecular ion and how we can determine or calculate molecular formulas from isotopic abundances, and how we could use high resolution mass spectrometry if we have the instrumentation to do that. And then we started talking about what happens to that molecular ion after it's generated. And in electron impact ionization, it does put in a lot of energy into that molecular ion, so it fragments a lot. So, in fact, we'll get to that. Electron impact ionization is thought of as a hard ionization method, meaning that it puts in lots of energy. And there's pros and cons to that. So we started talking about fragmentation, and we talked about several different mechanisms, and then we started going through and we looked at some functional groups and how they might fragment. So we're going to, we'll continue a little bit of that, but we're going to more like look at some examples now, a few examples. And then we're going to spend a little bit of time going on and talking about other ionization methods, just kind of very briefly. And we're going to talk just even more briefly, probably, because this is not really my strong point, is the instrumental side, the different ion separation methods. Right? Okay, so let's just work through a few examples here. So let's take this spectrum and try to assign it to one of those three molecules. So what would we do first?
Well, you find out, yeah.
First, we have to determine whether that highest mass ion is actually the molecular ion.
Yeah.
So how do we, if we didn't have the structures up there, how would we tell? Or could we tell?
You really can't.
No, but there is a hint here. I think the fact that this is an even mass, right? And we see that both of these fragment ions are odd masses. So that's at least consistent with this being an odd electron ion. And both of these being even electron ions.
Yeah.
Okay? So another way that we could discern whether this makes sense, that this is the molecular ion and these are fragment ions, is just look at the losses and see if they come out to be reasonable losses, right? So if we go from 86 to 57,
29.
minus 29. Right? And so that could be what? Loss of an ethyl group. And we could just look at, I guess in this case, here's 29, so this could actually be an ethyl cation too. And this would be, I guess, loss of 57, right?
Mm-hmm.
Okay, so let's look at the molecules then. So remember that the common fragmentation for carbonyls like this, ketones, if we have an R and R prime is this alpha cleavage where this comes down here, this goes like this, and we lose an R group. Okay, and we form this acylium type of ion. Okay, so for each of these, we could cleave here, and the ion and the charge would stay with the carbonyl. Right? So if all of these start with 86, this would be 43. This one would be 71. Here would also be 43 and 71. And here would be 57 on each side, right? So that's pretty simple then, right? So it's got to be this one. So let's just draw out how both the 57, so the 29 would have to be this way. So we can start with our ketone like this. So it can do its alpha cleavage this way. Excuse me. And we can draw this in a couple of different ways like we talked about last time. So this should be M over Z equals 57. Okay, so we can generate the 29 really in kind of two different ways. One is if we just draw a resonance here, easier to draw, where these electrons are up on the oxygen. And we'd have the plus here. We can do a subsequent cleavage, which was this heterolytic cleavage. So these electrons would go to the plus. And so we're going to lose a carbon monoxide group. And so this would end up being our ethyl group here. The other way that we can draw it is that if we actually draw a resonance here, where we have now the plus here, there's a radical up there, so we're just pushing the electrons up onto the oxygen, we can draw the same kind of heterolytic cleavage where this cleaves like this. And this would give us also M over Z equals 29. And the other piece, let's draw in the other non-bonding electrons. So I had to do a little Lewis structure figuring here. So this would give us a radical here, which looks kind of weird, but you can actually take these two together, and so this is kind of resonance, I guess, and draw it like this. So it's an acyl radical instead of the cation. All right? Okay. All right, so a similar situation here, but with amines. So without adding anything up, we notice that we see two ions up here. This one's at 73, and this is at 72. If one of those is the molecular ion, which one has to be the molecular ion?
72.
We have one nitrogen
Oh, it's odd, so it's 70.
Right, so it has to be odd, right?
Yeah.
So 73 is going to be our molecular ion, is the odd electron ion, because there's an uneven number of nitrogens. Right, so 72 actually has to be some m minus 1. Right, so it's losing a hydrogen atom in the process. Then we could look at the other losses, right? So this one is at 58. So 73 to 58
15.
is a loss of 15. So we're just losing a methyl. And then we have this ion down at 30, right, which we talked about before, which was usually this ion.
30 is
At 30, right? Because that's the main one we see usually when it's a straight chain, amine. Okay, so the normal cleavage of amines is the alpha cleavage, right? So it starts with, so I'll just draw a separate one here, R1. Well, okay, that's fine. R prime, I'm going to put H here. We ionize on the nitrogen. This goes down, combines with this, and we cleave that. And we get an ion like this, right? Plus the radical. Okay, so we're losing 1 and we're losing 15, right? So I think any of these could actually lose 1, right? Because as long as there's an H on an alpha position, then we can draw that loss like this, right? So this would cleave here, and this would give us 72. All right, so where else would this cleave? What else would it lose?
On C, would it lose that propyl off?
Would it lose the whole propyl? If we do a similar cleavage here, would it lose this whole thing?
Well, no. It would only lose a methyl.
It would lose a methyl,
Yeah.
right? So an analogous alpha cleavage would lose a methyl here, and this would give us 58. Okay. What about B?
You'd also get 58. No, you wouldn't. No, you wouldn't, because you're actually losing.
We could lose an H.
Yeah, but you would also lose potentially an actual propyl.
An propyl. Right. So that would give us 30. No, why did I write that like that? Not 27, but 72. Okay, and what about the last one? A, well, the first one. H, we could lose that. 72.
Losing ethyl.
And ethyl. That would be minus 29. So what would that give us? Probably something down in there.
44.
44. Let you guys do the math. Anything else?
You could also lose a methyl.
And a methyl.
Yeah.
Right, and that would be 58. Okay, so if we look at these three, which one do you think looks the best?
A.
A?
Mm-hmm.
If we got A, so we have a 58 and a 72, but we don't have much 44.
That's 43. That
We
okay.
can't.
I counted wrong.
Mm-hmm. So we don't really have this,
Yeah.
right? If we look at B, we have 30, and we have 72,
But we don't have 58.
but no 58. No 58. And for C, we have 72, and we have a big 58, which makes sense, but we don't see, at least from these cleavages, a 30. Okay? So, usually you think of just these cleavages, but this can actually do, if we start with C, we can also do another subsequent cleavage. So let's draw this out. Okay, so this is like this. And if we do our alpha cleavage here, this gives us a double bond over here, like this. And this is at 58. All right, so this is kind of a similar situation to what we saw before when we had the ether. Oh, this has an ethyl over here, though. Remember, if we have an H here, with the ether, we had a mechanism where the hydrogen could be transferred over here, and this bond would be broken like this. So we can lose like an ethylene group. And if that happens, we end up with, what am I?
Third.
Oh, I have another H on there, don't I? We have H, and then we transferred another H onto there. Oh, I'm still not doing this quite right, am I? 30.
I mean, there isn't.
Oh, yeah.
An ethyl.
That's not 30, though. Oh, that's why. Okay, I did this the wrong way. Okay, I'm going to erase this. I did the first alpha cleavage on the wrong side.
Wait, we're looking at C, correct?
C, yes.
There's no ethyl on the right side. It's just a methyl, right?
Oh, it's just a methyl over there. Yeah. Okay, so let me draw that in as an H. Okay, so we're going to do our first cleavage over here to generate 72. Like this. So this is 72. So then we can do a similar thing like I was just trying to draw, except we're going to do it off of this isopropyl. So this goes over here, and this goes over here. So in this case, we have this double bond over here. We lost this whole isopropyl, really, and we have an H like that. Okay, so now we have equals 30. So it seems like we can do these when we have a double bond, after we've done an alpha cleavage, so in general, so let's see if we can generalize here. If we have some Y group, oxygen or nitrogen usually, and we've done an alpha cleavage, oops, and we can have whatever we want here, but it has to have an H at this beta position.
Donated to
alpha, beta. So we could have other R groups, coming off of either the alpha position or the beta position or longer, right? And so then what happens is that this H goes here, and we lose that whole, that whole substituent, yeah. Well, we just replace that whole group with a hydrogen.
It's a second cleavage.
The second cleavage, yeah. Which usually most of our ions are, in general, we're looking at just a single cleavage, but sometimes we can have subsequent ones like this. So let's see. So that's like that one. Oh yeah, if we did it, yeah, we can't do that subsequent cleavage on any of those other ones. So there is a way to generate some 30. If it was B, we would basically only have 30, and it'd be much stronger. And so we see these two, obviously, in 58 with two methyl groups at the alpha position, there's a chance to cleave either one of those. It makes sense that that's the base peak, right? And then we can generate 30 as kind of an afterthought here. So C should be the correct
How can we assign base peak?
How can we assign
Yeah.
it? Well, the base peak is generated by this alpha cleavage here, right? So this electron comes down here, and we lose a methyl group. So we can either lose this methyl group or this methyl group.
It increases the chance for.
Yeah, I think it just,
58.
yeah. And if we're, I guess the loss of hydrogen it's loss of a smaller group. This is loss of the larger radical here that we can lose, methyl versus H. So it favors the loss of the bigger one. All right. Okay, so here's another one. So this one, we don't have the structures, but we have the formula.
EC 77.
77, which was what again?
Yeah, it's a benzene ring.
Right. The phenyl cation.
Does it depend on the substitution or not, the phenyl cation?
Well, I think in order to generate this phenyl cation, it basically needs to be a mono-substituted, right? Because if we cleave off one substituent, if we have other substituents, then it's not going to be 77. It's going to be the phenyl cation with whatever's left on the ring.
So you lose 15.
Okay.
There has to be an easy way to lose a methyl.
Methyl.
And the best way to do that is to have a ketone.
Okay. We got one oxygen.
Yeah.
How many unsaturations?
5.
5. Okay, so that makes sense to have a benzene and a ketone.
How do you say that you have a ketone?
Well, we just have, so far what we know is that we have 5 unsaturations, we have a benzene, so that's C6H5, right? We also have a methyl, so all that's left is a carbon and an oxygen. Right, so all we can really have is just acetophenone like this. Right, so how do we generate the 105 and the 77? How would we draw it out?
Well, you would make Are you saying mechanism-wise?
Yeah, mechanism-wise.
I mean, you'd make it an acylium ion.
Right, so we do this alpha cleavage like this. And this would be this plus. Okay, so this would be 105.
What's the name of this one? Phenylacylium ion?
Yeah, I don't know I guess.
The resonance, right?
Yeah.
Sure.
Right, we could draw that resonance where these go up here. And then we could just do the heterolytic cleavage. So these electrons go onto the carbon and we lose carbon monoxide. So losing these small neutral molecules is favored. And we get to the phenylcation, 77. Okay, the other way to draw it would be like we did before, to draw the resonance up here. So this is going to be the cation, and this is the radical up here. And then we could just do this heterolytic cleavage like this, and this would also go to 77. Right, so we can get there in a single cleavage or in two separate steps.
But the most abundant one is the first one that produced 105 probably.
Yeah, that is the base peak, 105. Partly because I guess maybe that acylium ion at 105 is in conjugation with the benzene ring as well. So maybe that's the most stable ion.
Oh, acylium ion, you mean?
Yeah, this one here.
Oh, yeah, that feels.
Or this one here. And then some of these smaller ones, I don't even know how they're really formed, but like this 51, I don't know if our book, in that McClafferty book, they have, for different types of groups, they have what they call an ion series. And so like for a benzene, like this monosubstituted, they might have even, a series of ions that you might see. And you kind of match those. So something like 51, it has to be actually the benzene ring has to break apart to get down to that point. All right, well, that was easy. All right. So this one is one that we worked on before, right? So we did we calculated out molecular or formulas for both of these two, and so 154 ended up being C8 H10 OS. And remember that 139 ended up being C7 H7OS. Right, so we lose a methyl group. And so let's see here. So the unsaturations for this molecular ion, what would that be? 4. And so we're going to lose a methyl. We have to then probably have a benzene ring. Well, I'm just guessing because of the unsaturations. Right, we don't see any 77s, so we don't have a mono-substituted benzene ring at least, right?
That's true.
Anything else that stands out to you when you look at the spectrum? If you can read those.
Loss probably from 154 to...
This one is minus 15. That's what we figured out before.
Yeah.
What about this one?
7.
Well,
That's a 126.
so what? 28.
Oh, 13.
28. Right, and it's going from an even mass to another even mass.
We should go from the base peak to the other ones, or from each peak to the previous?
Well, it's not so much from the base peak, because in this case it just happens that the base peak is the molecular ion. Right, so we're not going to really ever cleave things purposely from the base peak. It would be from the molecular ion, right?
But how do we know it's not produced from the secondary cleavage?
We don't really know, but I think we'd probably try to figure it out first from the molecular ion. Yeah. So what about this loss of 28? What do we know about that?
I mean, a loss of 13 is...
Right, yeah. So if we wanted to try to go this way, loss of 13 is probably one of those, there's not really any way to do that, right? Because it's one bigger than carbon, but we can't add any other groups on there. And we're not going to lose a CH group.
Hey, so John, what is the mass of sulfur?
32.
32? Oh, then no.
Right, so yeah, that one can't happen.
Oh, if it's a oxygen plus a CH2.
Is 28 as well.
Yeah.
Right, so 28 can be CO. What else?
Oh, and ethene.
Yeah, CH2, CH2. Both of those are reasonable losses, right?
Yeah.
So one thing we could try, but this didn't end up, I hadn't done it before, but I did it this morning. Let's look at this 26 and see if we can come up with a formula for it. For 126. And so, because if we could figure that out, that would tell us what type of group we're losing. So we'd have to go 126, 127, 130. So there's here. Oh, what am I doing? 130. 128. Okay, so 52, 4.5, and 2.6. Now, the one thing that could throw us off a little bit here is that there's this peak right here just below, at 125. So if that's an ion, it's going to have some contribution. Its M plus 1 peak is going to have a contribution to the 126, right? So it's not really an isolated ion like we'd like to see. So what would we have to do first to try to calculate the formula? Normalize it, right? Okay, so I've done that already. So this would be up to 100. This comes out to 8.65 and 5.0. Okay, so what do we look for first?
126. Maybe the carbon? No. For S probably.
Right, so we want to look for the A plus 2, and we have 5 there, and we know there's a sulfur in the beginning, so that means that really there has to be a sulfur still left in this ion. Right, so we haven't lost the sulfur yet. 0.8 and 4.4. Okay, so that leaves us at 7.85 for carbon.
Yep.
So we want to look for carbon now. How many?
0.6 for.
Yeah, and 0.6 for M plus 2. So how many carbons?
You got 7 of them.
7, right? 7.7 and 0.25. So let's just look at the remainder now. And we would have 0.15 and 0.35.
Wait, yeah.
So what do you think now? What should we do next?
Find if you can oxygen.
Maybe, yeah. It can fit an oxygen in there. Well, with our isotopic abundance, what else could we check?
If you can add all of the hydrogens up.
Right, so let's add these up, right? And see if we have enough mass room for oxygen.
Oh, you mean that we may have lost the oxygen in other cleavage?
84 plus 32 is 116.
116. All right, we're going to 126. Do we have room for an oxygen?
No.
No. So what do we have?
Just hydrogen.
Just hydrogen, right? So we have to have 10 hydrogens. Right, so this has to be C7H10S. So we have, in fact, we've kept the sulfur, but lost the oxygen. So it seems like those two might be separate then, right? So we need to be able to lose a methyl. We need to be able to lose an ethylene. And then somehow we're going to lose an oxygen too. So I'm just going to draw something in here.
Well, CO.
Or CO.
Yeah.
Right.
Yeah, okay.
Right. Because is that what I drew there? Right, so this would be lost. This is lost, then, well, or CO. But what do we know from our formulas? Yeah, you're right.
We have lost a CO.
So from here, this 28 is going from here to here. So this is a loss of CO, not a loss of ethylene. So yeah, this was a little tricky because when I was working on it, because I think the structure like I drew, okay, I'm going to draw like this. And I think that this is, and then I just had an oxygen over here somewhere, a phenol. So there is a mechanism to lose CO from phenols.
I don't like that.
So I thought something like this would work well because we can certainly lose a methyl from this, right? Alpha cleavage from the sulfur. So this gives us
So what is the structure of C7H7S?
what? So this would be 139. But, so I thought that this one was good because as well, if we didn't do this last calculation, I don't need to put that exactly in that position. We don't know that. So just somewhere here. It seemed like if we had this kind of system here as well,
Donation of the hydrogen.
well, we could do like a McLafferty kind of reaction here. So that would be like this. This would transfer there. This would cleave here, and this would go here. So this would give us this, which would be at 126 loss of an ethylene. But that doesn't seem to fit our calculation. Though I guess if we went, I didn't do that, if we went with only C6, then our carbon would be off, but our oxygen would be, isotope would be closer, right? So I'm not sure if it's a possibility that we'd have both of those. But here, let me add one in, and I'll show you this. Let's see, does it matter that oxygen is... does it add in a... But we see a tiny amount of 125. So I don't know if we could be generating a small amount of that.
What is that? It is a high energy environment.
It is, yeah. All right. I don't know about the 97. That'll be your assignment.
Sure, there we go.
All right, so page. All right, so let's start. I'm gonna draw this, and I'm gonna have the sulfur down here. I can't remember if it matters if it's there or not. Okay, so we're going to ionize here on the oxygen. Oops. Okay, and let me see if I can follow this. This is going to be the loss of CO from the benzene ring. It probably takes more time here than it's worth it. Must have hit it with my hand. Okay, so the hydrogen is going to be transferred onto the benzene ring.
So you want to justify the loss of carbon monoxide from...
Yes, right. But this isn't one that I would predict or that we'd really come up with on our own, I think. Radical. I guess this has another one up here. So all we've done here is move a hydrogen atom onto the ring. And we didn't even really use that radical to push this. So then this radical is going to be used to actually break the ring open. Oops, dang. Stop. Okay, so this is going to be... All right, so we just ended up breaking this bond right here.
Another breaking is going to happen, or you all have a resonance from this side?
Well, we could have some resonance over here, but we've actually broken the benzene ring, okay? Because we need to be able to do that in order to, to get rid of the carbon monoxide. Okay, so the next step here closes up the ring again, but into a 5-membered ring. Okay, so this gives us oops. Oh. No, I did that wrong. Sorry. I should put that up here. C O plus. And we have an H there. H. And the sulfur. All right, so now we're ready to lose the carbon monoxide. Right, so this can just come off like this. Plus here. And so we're losing CO. And this, in fact, adds up to 126. That doesn't seem and so it's still an odd electron ion. Though it's done a whole ton of, well, yeah, that's what we want for an even mass. I know I had another step drawn here where it lost a hydrogen atom, but that doesn't, I don't think that makes sense now. Loss of this to form another double bond here with a radical from this and this, but then that makes a cyclopentadienyl cation, which is actually anti-aromatic. So that's unlikely. You know, I guess when I looked at it before, I was like, oh, but I didn't think about it. The anion is the aromatic one. And we see 126. Some kind of crazy things can happen in there. But this, I guess it didn't really matter. What it didn't tell us here really is where that thioethyl group was, because that doesn't seem to play a role in this. This is just the loss of a carbon monoxide from a phenol, right? So that's kind of the important thing here. So you could, keep that in mind for other times if you see a phenol, and you see another, odd electron ion that oh, that has to be a rearrangement, and you calculate out, loss of 28 could be loss of a carbon monoxide. I'll have to look for a problem that fits in like that. Draw the mechanism for the loss of carbon monoxide.
When I saw this mechanism, like it has to be an exam question.
Too bad you're not taking organic cumes. I could put it on there too.
I feel like I would actually be doing better.
All right, so that's really all of the fragmentations and mechanisms that we're gonna specifically go through. Okay, so now we're just gonna kind of try to tidy up our mass spec understanding a little bit, because we've really focused on electron impact, but oftentimes these days that's not the method that people use. Depending on, it's because oftentimes they're not really trying to do this level of structure determination and using mass spec for that. So if we think about other ionization methods, let's think about first, why would we even need any methods other than electron impact? Because I think that was one of the first ones that was developed as well. So let's look at the advantages and disadvantages of electron impact ionization. So an advantage is that it's very sensitive, so you can do it with very small amounts of material. It's very reproducible, which makes it very good for matching to spectra in databases. Okay, so that's a real good thing. It works very well for volatile samples, because we have to be able to put them into the ion chamber and then just volatilize them, because it's a gas phase method. And it induces significant fragmentation, so we can do structure determination with it. We get more than just a formula. The disadvantages are sometimes things that were also advantages, right? So one disadvantage could be that it does not only that it works well with volatile samples, but it requires volatile samples. So things that are not volatile, meaning that they're either polar, much more polar, meaning there's more intramolecular forces and they get a higher boiling point, or they're big. If the mass just gets too big, then it doesn't volatilize as easily. And another disadvantage is that it induces significant fragmentation, which means that sometimes we don't see a molecular ion.
Sometimes we don't.
Right. So if we're not seeing a molecular ion, we may need to use a different technique to be able to observe that. Okay? So our needs. We want to be able to go to a higher mass, more polar compounds, and both of these essentially add up to being non-volatile. So we want to be able to do mass spec on less volatile samples. Okay? We want to have a strong molecular ion. Right, because that might be why we use this method. So really, all of the other techniques that we're going to look at would be considered to be soft. Yes.
I didn't understand a strong molecular ion. What do you mean by that?
We want an observable one. Ideally, the molecular ion might be the base peak, right? We don't want one so small or not existent at all. Yeah. We at least want to have an observable molecular ion. Okay, so we are going to go through some different methods. The first ones, we've already looked at electron ionization, but these first two methods, electron ionization and chemical ionization, are both considered gas phase methods. The next two, fast atom bombardment and matrix-assisted laser desorption, so Fab and MALDI are called desorption methods. And the last one is an evaporative method, is the electrospray, which may be... So have you run mass spec on any of your samples?
ESI.
Yeah, so you've used electrospray.
Yeah. Well, yeah. With bromocyclooctane.
Oh.
Yeah. Yeah. So yeah, I use. Ideally, if I were to have a GCMS, I would run that for all of my CH functionalization samples.
Right, because they're small enough and volatile enough.
Yep.
Right,
Yep.
and then usually GCMS uses EI.
Well, actually, I checked the Shimadzu.
Mm-hmm.
They use up there is ESI.
Really?
Yeah.
Oh.
Which was weird.
Okay.
Yeah.
All right. Yeah. So what I'm thinking, since we're kind of changing gears here, why don't we just stop now? We'll stop early for spring break. 10 minutes.
There you go.
And then we can run through these, and we'll go through the ion separation methods, and we can do those all together instead of starting and splitting it up. And then really once we've finished that stuff, well, I think then next time, so Wednesday after spring break, then I'll have the next homework assignment for you, so we can start to mix in mass spec with what we've learned already as well. And then we're going to start into two-dimensional NMR techniques.